Okay, everyone, welcome back to part 2 of this CAPE Physics Unit 2, Paper 1. We are solving the specimen paper from 2017 that CAPE provided us with, okay? So, question 16, a sinusoidal alternating current of peak value 20 amperes dissipates power of 50 watts in a resistor R. We're asked to find the value of the resistor, right? And so to do that, we can relate the current, the power, and the resistor by this formula that says P is equal to I squared R. Now, the important thing to note here is that this value of current that they gave us is actually our I naught, right? That's our peak value for current. And so we can't use that value, right, in calculating the power. We have to use the RMS value in calculating, that's what was used to calculate the power. And so if we want to find the resistor, the value of the resistor R, we'll have to find the peak, the RMS, right? So to find the RMS from that peak value of current, we do that the I naught, or the peak value, divided by the square root of 2. And so we end up with 20 being divided by the square root of 2, which is 14.14 amperes, right? So again, the RMS value is what we use in calculating the power. And so it's that value that we have to use to then find the value of the resistor. So we got our RMS to be 14.14 amperes. And so all we have to do at this point is rearrange this formula, making R the subject. And so that's what I did down here, where we now have R being equal to the power divided by I squared. And again, that I is our RMS that we calculated here. So we just do power is equal to 50, right? That's the power, which is equal to 50 divided by the RMS current squared, and we come out with 0.25 ohms for our value for that resistor, okay? So that's D here, so we select D and we are on our way. So now to question 17. It says, which of the following graphs best represent the IV, so the current voltage characteristics of a silicon PN junction diode? So that's a silicon, that's a semiconductor, right? That's our PN junction diode. No, we know it's not this, right? Because this is showing us kind of like an ohmic conductor, but just like with one part of it, just a positive part. We know that this is not it. This is not how our PN junction diode curve looks. We also know it's not this because this is showing some direct proportionality. So again, this is an ohmic conductor, and it's also showing a negative portion here, but this is for our ohmic conductor, which we know our semiconductor is not an ohmic conductor, right? So we can rule out A and B. So we come down to C now, and we see that we have our current here and we have our voltage here. And we see that at a voltage of 0.7, right? That's when we start to get some current flowing in this conductor. And so this is characteristic of semiconductors, right? Because what's happening is that initially, right, until you're at the point where you've applied enough potential to overcome the barrier potential, so you have to apply enough voltage to overcome the barrier potential in that junction diode before you can see current flowing, right? So in this case, we're in our forward bias mode, so we have a positive voltage, but until we apply enough voltage to overcome that barrier voltage, right, which is what this is, we won't see any current flowing. And so this is characteristic of what we would see for a semiconductor. And it turns out that the amount of voltage that we have to apply to overcome that barrier potential is around 0.7 volts, right, for semiconductors. So this kind of checks out, right, with what we're looking for. And then if we came down here and looked at this doesn't show those same characteristics, right? You still see that there's some potential, something to be overcome here, but this is not what we would see for our semiconductor and forward bias. And so we rule out this one as well. And so C is our answer, right? That is exactly how we would expect it to look for a semiconductor. So moving along to question 18. Question 18 says a direct current of 5 amperes dissipates heat in a given resistor at the same rate as a sinusoidal alternating current flowing through the same resistor, right? So the same rate. So effectively, so essentially they have the same power, right? So this DC 5 ampere current has the same power as an AC current. So it has, so the power is the same. Power is the same. Power, same. Power, same. Right? So the power is the same for the AC. AC current, central AC, as it is for the DC current. So they're asking, what is the RMS, the root mean square value of the alternating current? So in the definition of the root mean square value is that it is the value of the DC current, which gives the same power as the AC to a resistive load. So the question literally set us up here because it's telling us that this direct current of 5A dissipates heat in a given resistor at the same rate as a sinusoidal alternating current. So they have the same power is effectively what this is saying. So the current that gives us the same power is going to be the same, right, for the AC as the DC. So that's what this definition tells us. The value of the DC current, of the direct current, which gives us the same power as the AC, is what our RMS is. And so our RMS then will be 5 amps. So we look for 5 amps, that's B, and that's this one, right? So RMS is basically is equivalent to your DC current in a nutshell, right? Your RMS for AC current is the same as your DC value, which is 5 amps in this case. So that's how we end up with that, and that's correct. So moving on to question 19. Question 19 says that the ratio of the secondary turns to primary turns in an ideal transformer is 1 to 30. So that means that the ratio of our, so N2 to N1, right, is 1 to 30, right? So our secondary turns to primary turns, 1 to 30. So at a 120 volt AC supply is connected to the primary coil, and a load of 20 ohms is connected to the secondary coil. What is the secondary current? So they're asking us to find what? I secondary, and they're giving us that this is our V primary, and that they're giving this as our resistor, right, in our secondary coil. So that would be RS. So these are all the things that they give us. We know N2 to N1 is 1 to 30 from here. We know V primary or V1 is 120 volts, and we know RS, that is 20 ohms, right? So we have all these relationships that we can write for transformers, for ideal transformers, right? So one that we can pull on immediately, right, since we have a voltage here, is that V1 over V2 is equal to N1 over N2, right? And N1 is our primary coil, and N2 is the same as our secondary coil. V2 is our secondary voltage, and then V1 would be our primary voltage, right? So the voltage of the primary coil is 120 volts, so we can put that over here. Voltage of our secondary coil, we don't know, so that's an unknown here, right? So that's our secondary coil, our unknown is here. But we do know how many turns, right? We know that in our primary coil, there are 30 turns, and we know that in our secondary coil, as per the question, it's 1 to 30, right? Secondary to primary, 1 to 30. So the number of primary coils is 30. So we put that here. And so, yeah, so we have, going back up here, we have our voltage of 120 for the primary coil. Secondary voltage, we don't know. We know the number of turns in our primary coil is 30, and the number of turns in our secondary coil is 1. So we just rearrange this to solve for the voltage in our secondary coil, or V2. So let me put VS here. VS here for consistency. It's our secondary coil, VS, which is V2, the same thing. And so we rearrange, making VS the subject from here. And when we do that, we do cross multiplication. We end up doing 120 divided by 30 is equal to 4 volts, right? So that's the voltage in our secondary coil. But remember now, it's current that we want, right? So the VS over RS is what's gonna give us our IS, right? So that the voltage in secondary coil that we got from here is 4. So that's 4 volts divided by the resistance of the secondary coil that they gave us to be 20. So we divide that by 20 ohms, and we're gonna come out with 0.2 amperes. So that's our answer. D is our answer here, right? So again, they gave us ratios, so we wrote down our ratios, and we know these relationships. So all we have to do is just transpose for the voltage in our secondary coil, and that's what we did. We got 4 volts, and then we could just do, okay, the current in the secondary coil is what they want us to find, and that would be the voltage in our secondary coil divided by the resistance of our secondary coil. And they gave us this. Question gave us this, and we calculated this. So all we had to do was to plug in those values, and we came out with our current, right? Current in that secondary coil, which is 0.2 amperes. So moving along to question 20 now. So item 20 refers to the following diagrams, right? So we see a diagram over here. We have an AC supply. We have one diode in here, and then we have our load here, and then we have a cathode ray oscilloscope one that's over here in our output, right? And then over here in figure 2, we have our AC supply, and we see that we have 4 diodes, right? So we have 4 diodes in this setup. And then of course we have our load here, and then our cathode ray oscilloscope, the second one, is attached here. So right now, when we look at this figure, we should write out what immediately jumps out at us, or what we remember. And the first thing is that this one, where there's one diode, right? Where there's one diode, we're gonna have half wave rectification, half wave rectification, right? And then here, where we have 4 diodes, we're gonna have a full wave rectification taking place of our input signal, right? So full wave rectification, because we have 4 diodes, right? So we have 4 diodes. So that's full wave, right? And then this one is half wave because we have 1 diode. Okay? So now let's see what the question is asking us. Now the question is saying, which of the following traces will be seen on the cathode ray oscilloscope in the case of figure 1 and in the case of figure 2? All right. So what are we looking for, guys? What we're looking for is that whenever we have full wave rectification, so say we have a cycle like this, right? So we have this and this, right? If we have half wave rectification, right, what's gonna happen is that only the positive half of it is what we will see on our oscilloscope. So we will end up with this, or negative halves are gonna be erased essentially. So let me draw another trough here. And so the negative part is gonna go away. So all of this is gonna go away, and we'll end up with just the positive part. So we'll see this in the case of a half wave rectification. In the case of a full wave rectification, right, we're gonna have the same. Let's draw 2 cycles, right? And so when it's full wave, right, full wave rectification, what we're gonna see is that these negative portions are actually then turned into positive portions. Instead of just erasing them altogether, we're gonna flip them up to the positive side. And so we'll end up getting a curve like this. We're gonna get bam, 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 bam. So we keep the positive parts, and then we flip the negative up. So we end up with this kind of an image on the oscilloscope, right? So let's look into the question and see what matches what we came up with. So we said in the half wave case, we'll have this, and in the full wave case, we'll have this. So let's see what matches that. Half wave case is for figure 1, right? So this is for figure 1. And then figure 2 would give us that. So far, they don't match. This doesn't match that. It matches this, but not this one. So this one is not our answer. And then in this case, this one, they're flipped, right? So again, this doesn't match what we came up with up here. And then down here, we don't get a flat line, and we wouldn't get, we got this for the figure 1, but for figure 2, we're looking for this, right? So that's not C. So let's look at D now. D matches ours, which is saying that figure 1, we have 2, we just have 2 crests here. And then in this case, we have 4 crests. So 2 crests and then 4 crests for figure 2. So this is our answer. So D is correct. Okay, so that's how we do this kind of analysis with our diode. So the first thing we do is just look at our figure. This is 1 diode, half wave. 4 diodes, full wave. And we just kind of look at the images to see which one would correspond to what we expect to happen. And that's our answer. And in this case, it's D. Okay.